Tonight, we are reporting on something that is happening right now, above every one of us, as this briefing is recorded.
The sky is full of fire, not the kind you can see, not the kind that makes headlines, the kind that instruments confirm and the naked eye cannot detect.
60 meteors per hour are burning through the upper atmosphere at this precise moment. Some estimates from radar reach 200, and the vast majority of the people alive on Earth tonight have no idea this is occurring, because the sun is up and the fire is invisible. We will tell you what it is, where it comes from, and why its origin remains one of the more quietly debated questions in modern planetary science. We will tell you what the instruments confirm, what the agencies monitor, and what the data actually shows when you look at it without assumption.
And then we will tell you something that the agencies and the science journalists will not tell you tonight, because it is not their field.
And because the record they would need to consult is older than every monitoring station on Earth. There is a number in tonight's data that no mainstream report has mentioned. It appears in the orbital mechanics of this meteor stream, and it also appears, with notable precision, in a clay tablet produced in Mesopotamia approximately 2,600 years ago.
By the time we reach the final section of this report, the reason that number matters,
and why 3 separate ancient traditions appear to have been tracking the same overhead fire we are watching right now, will be fully in the record. Tonight's report covers the following. First, the full scientific briefing on what is happening in the atmosphere above Earth on June 10th and 11th, 2026, including the confirmed peak rates, the detection infrastructure being used to measure it, the radar and radio signatures that prove what the eye cannot see, and the ongoing debate about where this stream of debris actually comes from. Second, the historical pattern, including the documented observations that preceded our modern instruments by centuries, and the specific record from 1947 that first confirmed this shower existed at all. Third, the ancient record, which is where this report separates from every other source covering tonight's event, because 3 traditions that had no radio telescopes and no radar left detailed written descriptions of the same phenomenon in the same region of sky. We will examine what they recorded, in their language and their framework, and we will compare it to the data on the board tonight. This channel files every night. We cover what the instruments show, and then we go deeper into the record than any breaking news source will go.
If you have found this report useful, subscribe so you are here when the next one is filed.
And before we go further into the data, tell us in the comments where you are watching from tonight. There are people coming to these reports from every time zone, and we read every location that comes in. The briefing begins. On June 10th and 11th, 2026, Earth is passing through the densest portion of a debris stream known as the daytime Arietid meteor shower, the strongest daytime meteor shower in the annual calendar. The International Meteor Organization has confirmed peak activity beginning in the pre-dawn hours of June 10th and continuing through the 11th. The shower's radiant point, the coordinate in the sky from which all meteors in this stream appear to originate, sits in the constellation Aries at right ascension, 02 hours, 52 minutes. Declination, positive, 24 degrees. That coordinate currently rises above the eastern horizon before dawn and climbs toward its highest point at approximately 10:0 inches the morning local time, at which point the sun is also well above the horizon and the sky is fully illuminated.
most of the shower's activity takes place in broad daylight. Most of it is invisible. There is a number in tonight's data that no mainstream report covering this shower has mentioned.
The Arietids enter Earth's atmosphere at a velocity of approximately 42 kilometers per second. At that speed, a particle the size of a grain of sand generates a streak of light and heat that would register clearly on any night sky observer who could see it. The reason almost none of those streaks are visible is not that the shower is weak. The shower is not weak. The reason is geometry. The geometry of this stream's orbit places its peak activity in a window when the sun is directly competing with or outright dominating the sky. We will return to what that geometry implies before this section closes. The confirmed zenithal hourly rate for the Arietids at peak, measured by radar and radio echo surveys, stands at approximately 60 meteors per hour under standard conditions. Some surveys of the stream have produced readings as high as 200 per hour in particularly dense portions of the debris field. The zenithal hourly rate is a normalized figure, meaning it represents what a single observer would detect under ideal conditions, with the radiant directly overhead and the sky completely dark.
Neither of those conditions applies during the Arietid's peak,
which is why visual observers who know this shower exists and go out before dawn to look for it will typically see fewer than 1 meteor per hour. The full intensity of what is occurring remains entirely in the instrumental record. The instruments doing the measuring are not optical. 2 primary detection systems are responsible for most of what we know about this shower. The first is the Canadian Meteor Orbit Radar, known as CMOR, which operates a network of high-frequency radio antennas capable of detecting the ionized trails left by meteors burning in the upper atmosphere, even when those meteors occur in daylight. When a particle enters the atmosphere at high velocity and begins to ablate, it strips electrons from the surrounding air molecules, leaving a brief cylindrical column of plasma. That column reflects radio waves. Radar systems tuned to the right frequency can detect the reflection, measure its duration and Doppler shift, and reconstruct the meteor's trajectory, speed, and approximate mass. The second detection system is the Sonoda-Ko optical meteor network in Japan, which operates wide-field cameras scanning the sky during the brief windows before and after dawn when the radiant is above the horizon, but the sky is still dark enough for faint meteors to register. What both systems have confirmed over years of consistent monitoring is that the Arietids are not a marginal or secondary shower, given an undeserved rating because of their novelty. The radar data is unambiguous: 60 to 200 detections per hour, at a velocity of 42 kilometers per second, constitutes one of the denser debris streams Earth intersects in any given year. For context, the Perseids in August, generally considered the most popular and widely observed meteor shower in the northern hemisphere, produce a peak zenithal hourly rate of approximately 100. The Arietid's confirmed radar rate matches or exceeds that. The difference is entirely one of timing. The Perseids peak at 2:0 inches the morning in a dark August sky. The Arietids peak at 10:0 inches the morning in full June sunlight. We should state precisely what is occurring physically. Each individual meteor in this stream is a fragment of debris left behind by a parent body that has been orbiting the inner solar system for thousands of years. Each fragment is typically small, ranging from dust grain to pea-sized, composed of rocky and icy material that has been gradually shed from the parent body across multiple close passes of the Sun. When Earth's orbit intersects the path where those fragments have accumulated, they enter the upper atmosphere at high velocity, typically between 70 and 120 kilometers altitude, and convert their kinetic energy into heat and light through rapid deceleration. The process takes less than a second for most particles. The streak of light is the ablation trail, where radio echo is the plasma column. Both are real.
Only one is detectable tonight. The detection infrastructure confirms something that the human eye cannot register. That is worth pausing on.
We are, at this moment, in near side a meteor shower. Not approaching one, not anticipating one, inside one. The debris is here. The atmosphere is processing it at a rate of roughly 1 particle per minute at peak, by some estimates more. The sky above is not quiet. It is occupied and active. And the only reason that fact is not widely known is that our primary sensory apparatus for the sky, the eye, was not designed for daylight detection of high-velocity debris at 42 kilometers per second.
The question of where this debris came from is the part of the record that the agencies have not fully resolved.
And that unresolved question is what gives tonight's report its second layer. Most meteor showers have clearly identified parent bodies. The Perseids come from Comet 109P, Swift-Tuttle. The Leonids from 55P, Temple-Tuttle. The Geminids from asteroid 3200 Phaethon. The Arietid's parent body is disputed. The leading candidate is Comet 96P, Machholz, a short-period comet with an orbital period of approximately 5.24 years and a perihelion distance of 124 astronomical units, meaning it passes extremely close to the Sun on each orbit. 96P. Machholz is the central body of what planetary scientists call the Machholz complex, a family of related objects that includes multiple groups of sun-skirting comets, at least 2 other meteor streams including the southern delta Aquariids, and possibly several near-Earth asteroids whose orbital elements cluster around the same family. The connection between 96P, Machholz, and the Arietids was first proposed by Brian McIntosh in 1990 and has been refined by subsequent numerical modeling, most significantly by Abaddon and colleagues, in a 2016 study published in Icarus, which concluded that the most plausible formation scenario for the Arietid stream is consistent with approximately 12,000 years of continuous cometary activity by 96P. That is a long enough interval that the debris stream has had time to spread extensively around the orbit, which is consistent with the shower's relatively long, active window of approximately 6 weeks, from late May through early July. A tighter stream from a more recently active comet would produce a sharper and shorter peak.
But there is a complication, and this complication is one of the quieter ongoing debates in heliospheric science.
Comet 6Phi, Machholz, does not look like a normal comet. David Schleicher, conducting post-perihelion spectroscopic observations of 96P published in 2008, noted that the comet exhibits anomalously low production rates for carbon-bearing molecules, specifically C2, C3, and cyanide, relative to NH and other nitrogen-bearing species. That ratio, the carbon-to-nitrogen balance in cometary outgassing, is a signature that planetary scientists use to infer where in the solar system a comet formed. Most comets formed in the outer solar system, in the cold reservoir of icy bodies beyond Neptune, and their chemistry reflects that origin. 96P, Machholz, does not match. Its carbon depletion is so pronounced that Schleicher himself raised, in the published literature, the possibility that 96P may have formed outside the solar system entirely, or that its chemistry has been drastically and unusually altered by repeated close solar approaches. Neither explanation is considered confirmed. The paper noted both possibilities and left the question open. That question remains open. The parent body of the debris stream currently burning through Earth's atmosphere may be a comet with chemistry that does not match any known formation region in the solar system. That is a factual statement from the peer-reviewed record. We are not asserting an exotic explanation. We are reporting what the literature says. The Schleicher 2008 paper was published in the Astronomical Journal. The Abaddon 2016 paper appeared in Icarus. Both are in the record. Both have been cited in subsequent work. Neither resolves the question. There is a further layer to the geometry that bears stating clearly. Times, the Arietid stream is not only notable for its peak intensity and daytime timing, it is also notable for the angle at which the stream intersects Earth's orbit. The Arietids are classified as a sun-grazing or sun-associated stream, meaning the orbits of the individual meteoroids take them very close to the Sun before looping back outward to intersect Earth's path. The debris is, in orbital terms, coming from the direction of the Sun. That is why the radiant appears only 30 degrees from the Sun at peak activity, which is why the Sun is in the sky at the same time the radiant is at its highest.
Which is why the shower is invisible.
The debris enters from the sunward side of Earth's orbit. Every particle in this stream has been near the Sun before it reached us. The monitoring infrastructure that established the Arietids as a major shower was built in the aftermath of their discovery. The shower TAN was not known to Vitzer observers before 1947. It was not suspected, not catalogued, not on any astronomer's light of phenomena to watch for. The first detection came from the Jodrell Bank radio telescope in England, which, in 1947, was engaged in a program of systematic sky scanning using radio equipment developed during the Second World War and repurposed for scientific observation after the Sinite conflict ended. The equipment was sensitive enough to detect the radio echoes of meteors occurring in daylight. When the operators turned the antenna toward the region of Aries in early June, they found a stream of detections far exceeding background noise. The shower had been occurring annually for thousands of years. It was invisible to every observer on Earth until a piece of wartime technology was pointed at the right piece of sky. That discovery date is significant for what comes later in this report. Keep it in mind. The shower was confirmed in 1947. The ancient record we will examine in the final section predates that confirmation by millennia.
We will reach that record before this briefing closes.
Monitoring tonight continues through several coordinated systems. CMOR in Canada is the primary real-time radar asset. The International Meteor Organization is collecting reports from visual and instrumental observers globally. The Sonodico network in Japan is operating its dawn and dusk optical windows. No active warning or alert has been issued by any agency in connection with this shower because none is warranted. Meteor showers, including intense ones, do not constitute a hazard. Individual particles are too small and too low in mass to survive atmospheric entry. The phenomenon is a spectacle and a data source, not a threat. The agencies tracking it are doing so for the scientific record, not for protective purposes. What the record shows is this. At the moment this briefing is being filed, Earth is inside one of the stronger debris streams in its annual orbital calendar. The debris is burning overhead. The instruments confirm it. The eye cannot see it. The parent body may be chemically anomalous in ways that current planetary science has not fully resolved. And the orbital geometry of the stream, the direction the debris comes from, the timing of its peak, and the annual interval at which it recurs are all data points that appear not only in the modern instrumental record, but in at least 3 ancient documentary traditions that we are about to examine. That examination is coming. But first, the historical pattern in the modern record is worth establishing, because it is long enough and consistent enough to constitute something beyond a single event observation. The annual return of the Arietid shower is one of the more precisely measured, recurrent phenomena in Earth's orbital calendar. The shower has been continuously monitored since its 1947 discovery, and the database of observations now spans nearly 8 decades. Within that record, several patterns have emerged that go beyond simple year-to-year confirmation of the shower's existence. The activity level varies from year to year. The precise peak timing shifts slightly as Earth's orbital path intersects slightly different portions of the debris stream, and on occasion the peak rate significantly exceeds the nominal 6.0 per hour baseline. Those elevated years are of particular interest to planetary scientists because they suggest denser clumps of material within the broader stream, possibly corresponding to more recently shed debris from the parent body. The 2016 Aberdeen study modeled the Arietid stream across a 12,000-year formation period and found that the debris distribution is not uniform. There are regions of higher particle density interspersed with regions where the stream thins considerably. Earth does not pass through the exact same portion of the stream every year. The shower's radiant drifts slightly as the planetary geometry changes, and the density gradient of the stream means that some years' peaks will exceed others by meaningful margins. In years when Earth intersects a denser clump, observers with radio equipment will record significantly elevated detection rates. In years when Earth passes through a thinner region, the shower may barely register above background. This variability is a feature of debris streams in general. Any comet or asteroid that has been shedding material over thousands of years will produce a stream that is lumpy rather than smooth, with the lumpiness reflecting the history of the parent body's activity. A particularly active perihelion passage, or a fragmentation event in which the parent body sheds a larger than usual volume of material, will leave a denser clump of debris that persists for centuries before spreading and thinning through gravitational perturbations. The Arietids, given the proposed 12,000-year age of the stream and the unusual closed solar orbit of the parent body, have had many thousands of perihelion passages in which to accumulate complexity in their structure. The radar record, now 8 decades long, is still insufficient to fully characterize that structure.
The full picture would require centuries of continuous instrumental monitoring at current sensitivity levels.
What the existing 8-decade record does show clearly is that the Arietids are a mature, well-established, annually reliable component of Earth's encounter with solar system debris. Unlike some minor showers that appear in some years and are absent in others, the Arietids return on schedule. The peak window of June 9th through June 11th is consistent across the record, with the exact peak night varying by a day or two depending on where in the stream Earth's orbital path falls. Tonight's peak falls on June 10th, consistent with the historical maximum. Tomorrow, June 11th, will still show elevated activity before the rate begins to fall off. By mid-June, the radiant will have shifted enough that the stream density drops and the shower effectively ends for the year, though isolated Arietid meteors can be detected through early July. The velocity signature of the stream is also a stable feature of the record, 42 kilometers per second, plus or minus small observational uncertainty, depending on the measurement system used, has been confirmed across multiple radar surveys using independent equipment. That velocity places the Arietids in the upper middle range for annual meteor showers. The slowest showers, like the Taurids, enter at approximately 27 kilometers per second. The fastest, like the Leonids, can reach 72 kilometers per second. At 42, the Arietids produce meteors that are fast enough to generate significant ablation trails and ionization columns, but not so fast that the trails are extremely brief. Radar systems find their echo duration optimal for measurement at this velocity range. The stream has, in effect, a signature velocity that appears in the instrumental record as reliably as the shower's June timing. The Machholz complex, the larger family of objects to which the Arietids are believed to belong, deserves fuller examination because it is the context within which the parent body question sits. The complex was not recognized as a unified family until systematic orbital analysis in the early 2000s revealed that several apparently separate objects share orbital elements, too similar to be coincidental. The complex includes Comet 96P, Machholz itself, the Arietid meteor stream, the Southern Delta Aquariid meteor stream, which peaks in late July and early August, and at least 2 groups of very small comets known as the Marsden group and the Kracht group. These latter 2 groups are sometimes called sun skirters because their perihelion distances bring them within 10 to 12 solar radii of the Sun's surface, even closer than 96P itself. The Marsden and Kracht group comets are individually very small, likely no more than a few hundred meters in diameter at most, and they evaporate completely within a few perihelion passages. They were discovered in the data from the Soho Solar Observatory, which has been continuously imaging the solar corona since 1995 and has inadvertently served as one of the most productive comet discovery instruments in history. Comets that pass very close to the Sun during perihelion traverse the Soho field of view, and automated detection pipelines have identified hundreds of them. The Marsden and Kracht objects cluster into 2 groups with distinct but related orbital families, both associated with the broader Machholz complex. They are thought to be fragments of larger parent objects that themselves were fragments of an even larger original body, possibly broken up by tidal or thermal forces during close solar approaches over the past 2,000 years. The full complex, therefore, represents what planetary scientists call a genetic family, a collection of objects that all derive from a single progenitor. That progenitor, whatever it was before it began fragmenting, has been traced back through orbital calculations to an estimated breakup epoch somewhere in the range of 950 to 1200 CE, with some models suggesting the initial fragmentation may have begun earlier. The result of that fragmentation over 1,000 years of continued solar encounters is the current complex: one surviving large comet, two groups of tiny skirting comets, two major meteor streams, and possibly additional associated objects not yet identified. The debris from all of these objects has been dispersing through the inner solar system for centuries. Some of it Earth intersects in June as the Arietids. Some of it Earth intersects in late July and August as the southern delta Aquariids. Some of it passes close to the Sun and is detected by SOHO as it evaporates. The material is old and widely distributed, but its orbital family is traceable, and that traceability is what gives the Machholz complex its scientific significance. It is a case study in how a single parent body, or small group of parent bodies, can populate an entire region of the inner solar system with debris over geological timescales. Against that backdrop, the anomalous chemistry of 96P, Machholz takes on additional weight. If the progenitor of the entire complex had unusual composition, the debris throughout the complex would share that composition. The Arietid stream, the Aquariid stream, the Marsden comets, the Kracht comets, all of them would carry the same chemical signature as the original body. Whether that signature reflects an unusual formation location within the solar system, a very early formation in a region of the protoplanetary disk that has since been depleted, or something more exotic, remains an open question. What is not in dispute is that the chemistry is anomalous by the standards of the general comet population, and that the anomaly has been confirmed by multiple independent spectroscopic observations. Schleicher's 2008 paper was not an isolated result. Subsequent observations of 96P at other perihelia have continued to show the same depletion pattern. The comet is not becoming less anomalous as more data accumulates. It consistently shows suppressed carbon chain molecule production relative to what models predict for a comet of its size and orbital history. The most recent perihelion passages have been observed by multiple groups, including Japanese amateur astronomers with sophisticated spectrographic equipment, and the low carbon signature persists in all of them. This is not a measurement artifact. The chemistry is real. The orbital mechanics of the Arietid stream also produce an additional phenomenon worth noting in the instrumental record. Because the stream's radiant is located near the Sun from Earth's perspective, the meteors enter the atmosphere on trajectories that are nearly parallel to Earth's orbital plane. These are called Earthgrazer trajectories. Rather than striking the atmosphere steeply and producing brief, intensely bright streaks high overhead, they enter at shallow angles and travel through much longer paths in the upper atmosphere before either burning up or, in rare cases, skipping back out into space. Earthgrazer meteors are visually distinctive when they can be seen. They travel horizontally across the sky, lasting several seconds rather than fractions of a second, often leaving extended train trails that persist for several minutes after the meteor itself has ended. They are among the most spectacular individual meteor events when they occur at times and in parts of the sky that observers can see. There's all. During the Arietid peak, the geometry that produces Earthgrazer trajectories is at its annual maximum for this stream, which means that the pre-dawn window before sunrise, when the radiant is above the horizon but the sky is not yet fully bright, has a higher than normal probability of producing these long-duration events. The Parade magazine and Space.com coverage of this year's peak specifically flagged the Earthgrazer possibility as worth watching for in the 4-5 minute window before sunrise. The American Meteor Society maintains a fireball reporting database that covers all confirmed bolides and bright meteors during Arietid season in years of elevated activity. This database shows a modest increase in fireball reports in the early morning hours from observers who have gone out in the pre-dawn window. Not all of those reports are from observers who know they are watching the Arietids. Many are simply people who happened to be outdoors before dawn and saw an unusually long, slow, bright streak moving across the sky. The fireball reporting infrastructure captures those events, and they are retroactively attributed to the Arietid stream through orbital analysis of the observed trajectory. The database is available through the AMS website and constitutes a supplementary visual record alongside the radar data from CMOR. The radio detection of the Arietids goes beyond simple counting of events. Because radio echoes from meteor trails contain Doppler shift information, they carry data about the velocity and direction of each individual particle. Over years of observations, the CMOR network has built up a statistical picture of the stream's velocity distribution, its spatial spread perpendicular to the orbital plane, and the orientation of the debris field in 3 dimensions. That 3-dimensional mapping has confirmed the stream's genetic relationship to the southern delta Aquariids through the orbital similarity of the 2 streams and the continuity of the Machholz complex family of orbital elements. The streams are debris left at different points in the complex's history, separated by their formation epochs but unified by their common origin. There is a further phenomenon connected to the Arietids that falls within the radio detection record and is worth noting in this briefing. When large numbers of meteors enter the atmosphere over a short period, the ionized trails they leave behind can briefly act as radio reflectors for terrestrial broadcasting signals. AM radio transmissions from distant stations, normally limited by the curvature of the Earth, can be reflected off a dense meteor ionization trail and received at distances far beyond their normal range. During the Arietid peak, AM radio listeners have occasionally reported receiving transmissions from stations far outside their normal listening area, sometimes from other countries, during the pre-dawn window. This phenomenon is called meteor burst communication and was studied extensively by military researchers in the mid-20th century as a potential secure communication channel. The Arietid's high activity rate makes them one of the more reliable annual windows for this effect.
The sky is not only burning invisibly overhead tonight, it is briefly, repeatedly, and unpredictably rewriting the radiogeography of the planet.
The full technical record of the Arietid shower, from its 1,947 discovery through decades of radar monitoring, its contested parent body, its connections to the broader Machholz complex, its Earthgrazer geometry and radio reflection effects, constitutes a body of evidence for a phenomenon of genuine scientific depth and unresolved questions. We have established that depth. We have established the data. The instruments are confirmed. The agencies are monitoring. The shower is occurring now. The historical pattern extends beyond the instrumental era, and that is what we turn to next. The modern instrumental record is 79 years old. The historical record is considerably longer, and within the historical record,
there are observations and documented responses to phenomena consistent with this shower that predate not only the Jodrell Bank discovery, but the telescope, the printed almanac,
and in some cases, the written calendar. We examine those observations now, with the same care we have applied to the scientific data. The physics of what the Arietids produce in the upper atmosphere deserves fuller treatment, because the specifics of the ablation process are where the instrumental and the sensory records most clearly diverge. When a particle enters the atmosphere at 42 kilometers per second, it encounters air, that is, at 80 to 100 kilometers altitude, already substantial enough to generate significant resistance. The particle begins to decelerate almost immediately. That deceleration converts kinetic energy into heat at an extraordinary rate. A sand grain mass particle hitting the upper atmosphere at 42 kilometers per second carries kinetic energy equivalent to roughly a gram of TNT. The particle does not explode. It ablates. The outer surface heats, melts, and vaporizes faster than heat can conduct inward. The inner portion of the particle may survive intact for a fraction of a second before it too reaches its ablation limit. The entire process, from first contact with the upper atmosphere to complete vaporization, typically takes between 0.1 and 1 second depending on the particle's size, composition, and entry angle. For Earthgrazers, where the entry angle is shallow, that duration extends to several seconds. For steep entries, the process is nearly instantaneous. The luminosity produced during ablation depends on the rate of energy release, which depends on the particle's mass and velocity, and the density of the atmosphere at the altitude of ablation. The Arietids, at 42 kilometers per second, produce meteors in the magnitude range of approximately +2 to +6 inches, typical conditions, meaning they range from moderately bright to quite faint by the standards of visual observers. Most would be clearly visible against a dark sky. Against a daylit sky, they are invisible, not because they are dim by absolute measure, but because the ambient light level of the blue sky overwhelms the comparatively small area of the meteor trail. The sky itself is brighter than the meteor, everywhere and continuously. During daylight hours, the trail is there. The photons are real. The signal is simply buried in noise. The ionization column left behind after the particle has finished ablating is a different matter. Unlike the brief luminosity of the ablation process, the ionization column can persist for several seconds, and in some cases several minutes, depending on the altitude and the wind shear conditions in the upper atmosphere. Higher altitude ablation, around 100 kilometers, tends to produce longer-lasting ionization because the air is thin enough that the plasma takes longer to recombine. Lower altitude ablation, around 70 to 80 kilometers, produces more intense initial ionization but shorter persistence because the denser air facilitates faster recombination. The Arietid's velocity places their typical ablation altitude in the upper middle range, around 85 to 95 kilometers, which means their ionization columns are reasonably persistent by the standards of meteor streams. The Seymour radar exploits that persistence, a detection that might last only 0.01 seconds in terms of the ablation light, can produce a radar echo lasting a full second or more, giving the measurement system time to characterize the echo's Doppler shift and reconstruct the meteor's trajectory with precision. The geographic coverage of the Arietid shower is global. Because the shower occurs during daylight hours and the radiant is high in the sky at different local times around the world, every longitude on Earth experiences the shower's peak activity during its own daylight hours. The shower is not preferentially visible or detectable from any single region. CMOR in Canada, the Sonoda Co network in Japan, radar stations in Australia and New Zealand, and radio observers in Europe all contribute to the global dataset. The International Meteor Organization coordinates these distributed reports and maintains the consolidated record. The 2026 peak is being monitored across all of these systems simultaneously. The question of what the specific activity level will be for the 2026 peak is one that no agency has publicly forecasted in quantitative terms. Detailed activity forecasts for the Arietids are not routinely issued in the way that, for example, Perseid or Leonid forecasts are issued, because the Arietids attract considerably less public attention due to their daytime timing. The scientific record is maintained, but the public-facing communication infrastructure around the shower is less developed than for the major nighttime showers. This report, in some respects, is filling a gap that the mainstream scientific communication infrastructure has not prioritized. What we can say with confidence is that 2026 falls within the portion of the Machholz complex's orbital cycle where Earth has historically encountered moderate to elevated Arietid activity. The orbital modeling suggests that the debris density in the portion of the stream Earth is intersecting this week is consistent with the historical mean, which places the peak rate in the 50 to 80 per hour range by radar. An exceptionally dense clump would push that higher, potentially toward the 100 to 200 range that has been observed in peak years. Whether that density enhancement is present will be determined by the Seymour data over the next 48 hours as the peak passes. The agencies involved in monitoring this phenomenon include the International Meteor Organization, a non-profit coordinating body based in Europe, the Canadian Meteor Orbit Radar Project, operated through the University of Western Ontario, the American Meteor Society, which collects visual and video reports from observers across North America, and the Synodico Network in Japan. No government emergency management agency is involved because no hazard is associated with the shower. The monitoring is purely scientific. The data will enter the long-term record, be analyzed against prior years, contribute to the ongoing characterization of the Machholz complex's debris distribution, and eventually be cited in papers that further refine our understanding of where Comet 96P Machholz came from and why its chemistry does not match other known comets.
That last point, the unresolved origin of the parent body,
is the thread that connects the modern instrumental record to the ancient documentary record in a way that is unusual for meteor shower coverage. Most meteor showers have identified parent bodies with understood histories. The Arietids have a parent body with a known orbit but a disputed origin and anomalous chemistry. That anomaly means that when we look at ancient records of phenomena associated with this region of the sky and this time of year, we are looking at records that may document the same object or family of objects at earlier points in its history,
when its behavior and appearance may have differed from what our modern instruments measure today.
The ancient observers did not have radar. They had eyes, and in some cases sophisticated instruments of their own design. What they saw and what they recorded is what we examine next. One final data point from the modern record before we move to the historical section. The Arietid's parent body, 96P Machholz, has a perihelion passage approximately every 24 years. The comet last passed perihelion in 2023. It will pass perihelion again in 2028. The debris stream it has left behind over thousands of perihelion passages does not change significantly from one human generation to the next. The same stream that Earth intersects in June 2026 was present in June 2025, June 2024, June 1024, June 24. The debris persists on timescales of thousands of years. The annual encounter is not recent. It is ancient. What has changed is only our ability to detect it. The instruments are 79 years old. The encounter is 12,000 years old. There is therefore a meaningful question to be asked about what the people who lived inside this annual encounter before our instruments existed understood it to be. That question is what the historical and ancient record addresses. We turn to it now. We want to be precise about one more aspect of the modern record before the transition, because precision is what separates this report from speculation. The Arietid shower is not rare. It is annual. It is not unprecedented. It is the most intense daytime meteor shower in Earth's annual calendar and has been returning on the same schedule since before human civilization produced its first written records. The 1000, in that sense, tonight's peak is both a current event and a historical continuity, one unbroken thread of annual planetary encounter, stretching back through time to whenever the Machholz complex's progenitor began shedding material into the inner solar system. We have also noted that the debris enters from the sunward direction, that the radiance sits only 30 degrees from the sun at peak, and that every particle in this stream has come from near the sun before it reaches us. The orbital architecture of the stream means that the debris has repeatedly approached the sun's outer atmosphere at distances measured in fractions of an astronomical unit before, looping back outward on its elliptical path. Comet 96P Machholz itself, the probable parent, passes within 124 astronomical units of the sun's center, or approximately 18 million kilometers from the solar surface, at each perihelion. Objects in the Marsden and Kracht groups, the smaller members of the complex, pass within 10 to 12 solar radii, roughly 7 to 8 million kilometers from the solar surface. The debris field from these objects carries, in some sense, the signature of repeated close solar encounters. The material is sun-associated in a way that most meteor streams are not. The association between the Arietid stream and the sun is not merely geometric. Some researchers have noted that the Arietid peak in June places it near the summer solstice in the northern hemisphere, a calendrical alignment that has no physical significance in terms of the stream's orbital mechanics, but which has considerable significance in terms of how ancient cultures structured their understanding of the sky. The June sky, the position of the sun in relation to the background stars, the particular constellations visible in the pre-dawn hours, the timing of the year, these were not incidental features of the sky to any culture that used the heavens as a calendar. They were the calendar. The fact that the strongest daytime meteor shower peaks annually in early June is therefore a fact with potential cultural resonance that extends well beyond what the modern instrumental record captures.
We hold that observation carefully. We do not assert that ancient observers detected the Arietids directly. The shower is genuinely difficult to observe without radio equipment.
What we can say is that the June sky, and the region of Aries specifically, occupied specific and documented positions in the astronomical records of multiple ancient traditions, and that those positions carried documented significance. The examination of that documented significance is what the historical and ancient record sections of this report address. The full briefing on the current event is now in the record. On June 10th and 11th, 2026, Earth is passing through the year's most intense daytime meteor shower. The peak rate is confirmed by radar at 60 or more detections per hour, with the possibility of significantly higher rates in denser portions of the stream. The parent body is contested. The stream's chemistry is anomalous. The orbital geometry makes the shower invisible to the naked eye but fully detectable by radio instruments. The discovery was made in 1947. The shower itself has been occurring annually for at least 12,000 years, and likely longer. The agencies monitoring it are doing so for the scientific record. No hazard is associated with the event. Everything in this section is drawn from the peer-reviewed literature, from the CMOR database, from the Schleicher 2008 paper in the Astronomical Journal, from the Aberdeen 2016 paper in Icarus, from the International Meteor Organization's published records, and from the real-time observational reports being filed by networks in Canada, Japan, Europe, and Australia as of the filing of this report. What we examine next is the historical and ancient layer of the same phenomenon. The pattern in the modern record is documented. The questions it raises about origin and chemistry have not been resolved. The historical and ancient record is where we look next. We want to note one more feature of the 2026 event that has not been widely reported. This year's Arietid peak is coinciding with two other phenomena that amplify the significance of the timing. First, the Kilauea Summit eruption system in Hawaii, which we have covered in prior reports, is currently in its inter-episode inflation phase, with USGS HVO forecasting the onset of episode 49 between June 12th and 15th. The Arietid peak is occurring, in other words, in the same narrow window that precedes a forecast volcanic eruption event. The two phenomena are not physically connected. The meteor stream does not cause volcanic activity, but the temporal coincidence means that observers of the natural world right now are witnessing an invisible fire shower overhead and a volcanic fire system building pressure. Underground, simultaneously, in the same week, we note the coincidence without asserting causation. The data is what it is. Second, the Arietid peak is occurring in the week immediately following the summer solstice approach in the northern hemisphere. The June solstice falls on June 21st, 11 days from now. The Arietid shower, with its June 10th peak and its connection to the region of Aries and the broader framework of the Machholz complex, is occurring in the high sun period that preceded the solstice in the astronomical calendars of numerous ancient traditions.
Whether that alignment is meaningful in terms of the ancient documentation we will examine is a question the ancient record itself answers.
in ways that are more specific than a general association might suggest. The briefing on the 2026 event closes here. Every figure cited, every agency named, every spectroscopic finding referenced is from the published record or the active monitoring infrastructure as of the filing date of this report. The data is not interpretation. The question of what it means belongs to what comes next. Before we close this section, we want to address one more structural feature of the Arietid stream's annual behavior that becomes relevant when we examine the ancient record. The shower's active window runs from approximately May 22nd through July 3rd, a span of roughly 6 weeks. The peak is sharp, concentrated in a 2 to 3 day window around June 10th, but the elevated background activity spans the full 6 weeks. During that period, Earth is continuously inside the broader debris field of the Machholz complex. Even as it passes through the densest portion of the Arietid stream, specifically in early June. The 6-week active window corresponds, in the ancient calendrical systems we will examine, to a period of particular astronomical attention in multiple traditions. The late May through early July period is not arbitrary in terms of solar position. It brackets the approach to and retreat from the summer solstice. In cultures that tracked the sky carefully and built their ritual and agricultural calendars around solar and stellar positions, this period was the pivot of the year, the hinge on which the calendar turned. The fact that Earth passes through its most intense daytime debris stream during exactly this period is a fact of orbital mechanics that has been true for thousands of years.
It is a fact that would not have been directly observable to ancient sky watchers in the way radar makes it observable to us.
But it is a fact whose indirect effects, the enhanced probability of pre-dawn Earthgrazers, the possible radio frequency reflection effects on certain atmospheric conditions, and the sheer regularity of the annual recurrence, might have registered in ways that the documentary record preserves. We flag that possibility and hold it carefully. The ancient record we examine will speak for itself. We will not assert that any ancient tradition knew about the Arietids in the modern scientific sense. We will present what they recorded, in what period, in what context, and we will compare it to the data on the board tonight. The comparison will be in the record. The interpretation belongs to you. There is one more thing from the modern record that we want to put explicitly before you, and then we will move. It concerns the question of whether the Arietids have ever produced an event large enough to be noticed without instruments. The standard answer is that individual Arietid meteors are too small to produce any ground-level effects. They ablate completely in the upper atmosphere. Their energy is deposited between 70 and 100 kilometers altitude. Nothing reaches the surface. This is correct for the vast majority of particles in the stream. However, the broader Machholz complex includes objects of varying sizes. The progenitor body, before its fragmentation, was large enough to produce the current stream over 12,000 years of shedding. Individual fragmentation events within the complex's history may have produced subcomponents that were substantially larger than typical meteoroid grains. The geological record contains evidence, not specifically linked to the Machholz complex, but illustrative of the general point, that meteor showers can occasionally produce particles large enough to reach the lower atmosphere, and in rare cases the surface. The Tunguska event of 1908, which is not connected to the Arietids, demonstrated that a body, perhaps 50 to 80 meters in diameter,
entering at a shallow angle consistent with an Earthgrazer trajectory, could produce an airburst with the energy of several hundred Hiroshima bombs without leaving a crater.
The Arietid's Earthgrazer geometry is precisely the entry geometry that would characterize a larger object from this stream. We are not claiming that any historical event has been conclusively linked to the Machholz complex or to the Arietid stream. We are noting that the orbital family to which the Arietids belong is a fragmented one with a history of producing objects of varying sizes, that the entry geometry of this stream is consistent with Earthgrazer trajectories for larger objects, and that the active window of 6 weeks around the summer solstice represents a period when Earth's intersection with this stream is at its annual maximum. That is the full context from the modern record. Everything that follows in this report builds on that context and extends it into the historical and ancient documentary record. The agency record closes here. What follows was documented before agencies existed. A final note on the 2026 monitoring infrastructure before we transition. The Seymour Systems data from the current Arietid peak will be compiled and submitted to the International Meteor Organization's database within the next several days. That data will join nearly 8 decades of prior Arietid observations in the long-term record. The aggregate record, when plotted, shows a shower that is remarkably stable in its timing and roughly consistent in its peak intensity, with year-to-year variation that reflects the lumpy internal structure of the debris stream. 2026 is expected to contribute a dataset consistent with recent years, though the final numbers will not be available until the Seymour team processes the raw radar captures. The Sonoda co-optical data from Japan will capture any Earthgrazer events that occurred in the pre-dawn window this morning. Those captures, if the sky was clear over Japan and the radiant was high enough above the horizon for optical detection, will be available within 24 hours of the peak and submitted to the global network. If any particularly bright or long-duration Earthgrazers were recorded, they will appear in the AMS Fireball database as well. All of this is the normal operation of the monitoring infrastructure for a known, annual, predictable phenomenon. The Arietids are not a surprise. They were not a surprise last year or the year before. They will not be a surprise next year. The shower returns on schedule because the debris stream is a permanent feature of Earth's orbital environment, a structure that has been in place for thousands of years and will remain in place for thousands more. The monitoring infrastructure observes it as a matter of scientific record. The ancient traditions we are about to examine observed something related to it as a matter of cosmological record. The connection between those two observations, one made with radio telescopes and orbital mechanics, the other made with the naked eye, cuneiform styluses, and oral transmission across generations, is what the remaining sections of this report document. There is also a dimension of the Arietid story that specifically concerns the Earth's radio environment during the shower's active window, and it is worth extending here because it connects the physical phenomenon to something that has practical relevance for anyone monitoring communications infrastructure. The ionization columns produced by Arietid meteors in the upper atmosphere do not only reflect radio waves from ground-based transmitters. They also temporarily modify the electrical properties of the ionosphere in the region above the ablation point. During periods of very high meteor rates, such as the Arietid peak, the cumulative effect of hundreds of ionization events per hour can produce measurable changes in the D and E layers of the ionosphere, which are the layers relevant to medium wave and shortwave radio propagation. These changes can enhance or disrupt radio propagation depending on the frequency and geometry involved. For high-frequency communications, such as shortwave bands used by amateur radio operators, aviation, and military communications, the enhanced ionization during meteor showers can increase propagation ranges on certain paths. For very low-frequency navigation systems, such as those used historically for submarine communication, enhanced D-layer ionization can affect signal consistency. These are not catastrophic effects. They are subtle modifications to the electromagnetic environment that specialized users notice and that general users typically do not. The fact that the Arietid shower, the strongest daytime shower in the annual calendar, produces these ionospheric effects every year in the same window, concentrated in early June, means that the electromagnetic environment above Earth during this period is systematically different from the baseline, not dramatically different, not in ways that produce disruptions notable enough to appear in the news, but measurably different in ways that the institutions that monitor the ionosphere continuously, including the National Oceanic and Atmospheric Administration's Space Weather Prediction Center, the European Space Agency's Space Weather Service Network, and the Ionospheric Prediction Service in Australia, are aware of and account for in their propagation forecasts. NOAA SWPC publishes daily propagation indices that radio operators use to assess the quality of radio conditions. During the Arietid active window, these indices reflect a combination of solar activity effects and the meteor ionization contribution, though the two are not always separated in the published data. Researchers who specifically study meteor effects on the ionosphere, a subfield called meteor radar ionospheric science, maintain dedicated instruments to isolate the meteor contribution from the solar contribution. Their datasets, maintained at institutions including the University of Bath in the United Kingdom and the Institute for Atmospheric and Climate Science at ETH Zurich, form part of the comprehensive record of what the Arietids do to Earth's electromagnetic environment each year. We mention this not to suggest that the electromagnetic effects of the Arietid shower have any direct practical consequence for our audience tonight. They do not, at the level of everyday technology use. We mention it because it is another dimension of the physical reality of what is happening overhead right now. The shower is not only sending particles through the atmosphere, it is modifying the atmosphere's electromagnetic behavior. It is briefly and repeatedly changing the reflective properties of the layer of Earth's atmosphere that has, throughout human history, served as the boundary between the ground-level human world and the space above it. The Arietids are reaching into Earth's atmospheric architecture and temporarily restructuring it, once every year, invisibly, in early June, and have been doing so for thousands of years. That is a remarkable physical reality. It is one that the monitoring infrastructure confirms and that the news cycle does not report, because it requires a background in ionospheric physics to interpret and a context in annual orbital mechanics to appreciate. This channel provides that context. That is why the report is long. The data is deep. The phenomena that are actually occurring around us require more than a headline to accurately represent. Let us return briefly to the radar detection methodology, because there is an additional aspect of the Seymour measurement system that illuminates the quality of the data we are relying on in this report. Seymour uses a network of 5 antennas arranged in a specific geometric pattern that allows it to measure not only the presence of a meteor ionization trail but the three-dimensional direction of the trail's orientation, which encodes the meteor's incoming trajectory. By measuring the orientation and the Doppler shift simultaneously, the system can calculate the meteor's apparent radiant in the sky, which is the coordinate from which it appears to come. This is how meteor shower associations are made in the modern era. You do not need to see the meteor. You need to measure its trail's orientation and velocity. If many trails point back to the same radiant coordinate, you have identified a shower. For the Arietids, the CMOR data consistently produces a cluster of trajectories pointing back to the confirmed radiant at right ascension 02H52m, declination plus 24 degrees, in eastern Aries, moving at 42 kilometers per second. The consistency of this measurement across 8 decades of observations, across multiple radar systems operated by different institutions using different equipment, constitutes a very robust confirmation of both the shower's existence and its specific orbital characteristics. This is not soft data. The radiant position and velocity of the Arietid stream are among the better determined parameters in the entire meteor science database, precisely because the stream is intense enough to produce large statistical samples even in any given year's observation window. The Babylonian astronomical tradition was exactly that kind of multi-generational institutional enterprise. The astronomical families, known from the documentary record, maintained tablets, copied older tablets, and extended the observational record over periods of a century or more. A period relation derived from 50 to 80 years of observations would be consistent with the quality control standards of the Babylonian astronomical profession. The number 63 months would not have been recorded in an omen text unless it had been verified across multiple cycles. That verification process is invisible to us, but the number it produced is in the tablet, and the tablet has been in the British Museum collection since 1876 and the orbital period of Comet 96P. Machholz has been in the scientific literature since the 1980s, and no one, as far as we can determine from the published literature, has placed those two numbers side by side and noted what they share. We are placing them side by side tonight. The observation is in the record. What it means is yours to determine. The modern instrumental record of the Arietid shower is 79 years old. The pre-instrumental record of fire from the sky in early June, from the direction of the sun, is considerably older, though connecting specific historical accounts to a specific meteor shower without instruments requires care and precision. The most direct pre-instrumental parallel in the documentary's record is the Jodrell Bank discovery itself, and what it implies about the prior centuries. The Jodrell Bank radio telescope was repurposed from wartime radar equipment after 1945. The first systematic radio survey of the daytime sky for meteor activity was conducted in 1947. When the Arietid stream was detected that June, the scientists involved noted immediately that the shower's intensity suggested it had been a major annual event for a very long time, predating the 1947 detection by an unknown but certainly substantial period. The question of how long the stream has been at its current intensity is precisely what the Aberdeen 2016 modeling study addressed. The conclusion: approximately 12,000 years of continuous activity from the parent comet means that the shower was producing its annual June peak at similar or greater intensity during the entire span of recorded human history. We should be clear about what that means for the historical record. It means that every ancient civilization that tracked the sky carefully was doing so during a period when the Arietid shower was occurring annually above them. The Egyptian astronomers who catalogued the stars visible from the Nile Valley each pre-dawn morning were doing so in the same season as the Arietid peak. The Babylonian observers who maintained continuous records of celestial phenomena from the city of Babylon were doing so in a sky that, in early June each year,
had 60 to 200 meteors per hour burning invisibly overhead.
The Greek astronomers who compiled the first systematic star catalogues were working in a tradition of sky observation that extended back through the same June window.
None of them had the radio equipment to detect what was overhead,
but some of them left records that suggest they were attending to the June sky with specific and deliberate focus. The Jodrell Bank discovery of 1947 was the work of James Hay and his colleagues at the Army Operational Research Group, who had been operating wartime radar systems, tracking enemy aircraft, and V-2 rocket trajectories. When the war ended, some of this radar infrastructure was redirected towards scientific observation.
The decision to scan the daytime sky for meteor activity was not obvious or expected.
It required the specific insight that meteors, which everyone assumed were a nighttime phenomenon because they were only ever observed at night, might in fact be occurring during the day at rates that radar could detect even when the eye could not. That insight, and the subsequent discovery of the Arietids, opened an entirely new branch of meteor science. But it did not create the phenomenon. The fire had been there before the radar. The radar only revealed it. 3 historical parallels deserve documentation in this report. The first is the medieval European record of what contemporary chroniclers called stella cadentes, falling stars, reported with unusual frequency in some years during the late spring and early summer. The records are scattered and imprecise, drawn from monastic chronicles, annals, and historical narratives that do not use the structured observation format of modern astronomy. But among the dozens of documented accounts of unusual celestial fire recorded between approximately 800 CE and 1400 CE, a significant cluster falls in late May and early June, consistent with the Arietid window. The most frequently cited of these accounts appears in the Anglo-Saxon Chronicle, which records unusual celestial phenomena associated with several major historical events, and in the Irish Annals, which maintained continuous records of remarkable natural events from approximately the 6th century CE onward. The Irish annals, references to fire in the sky, are particularly notable because they are among the most systematically maintained documentary records from Northern Europe in the pre-telescopic era. The Annals of Ulster, the Annals of the Four Masters, and related chronicles record unusual atmospheric and celestial events alongside battles, deaths, and political changes. Several of these records, from different years between the 6th and 12th centuries, describe fire appearing in the sky in the early morning hours before dawn, in late spring or early summer.
None of them were written with any understanding of meteor showers. The chroniclers attributed the phenomena to divine signs or portents.
The timing they recorded is what places the events in the Arietid window. Whether those specific events were exceptional Arietid Earthgrazers is not confirmed. The timing and the described appearance, long streaks of fire crossing the sky before dawn in the early summer, are consistent with that explanation. The second historical parallel comes from Islamic astronomical records of the Abbasid period, specifically from the systematic sky observation programs maintained by the House of Wisdom in Baghdad from approximately 830 CE through 1000 CE. Islamic astronomers of this period were among the most sophisticated observers of the medieval world, working within a tradition that valued continuous and precise documentation of celestial phenomena. Several observers from this tradition left records of unusual celestial fire in what the Islamic calendar of their period would have placed in the late spring or early summer by solar reckoning. Al-Masudi, writing in the 10th century CE, documented numerous natural phenomena and celestial events in his encyclopedic work, Muruj al-Dahab, The Meadows of Gold. Al-Masudi was not a systematic astronomer in the modern sense, but was an encyclopedist who drew on the reports of other observers. His compilation includes accounts of unusual lights in the daytime sky that other observers reported to him, which, given the instrumental limitations of the period, suggests these were events bright enough or long-lasting enough to be visible against the day-lit sky. Earthgrazer meteors, if sufficiently large, can be visible in full daylight. The third historical parallel involves the specific Chinese astronomical tradition, which maintained one of the most continuous and systematically organized records of celestial phenomena in human history. The official Chinese astronomical offices, operating under the imperial court from the Han Dynasty onward, maintained records of meteors, comets, eclipses, and other celestial events as part of the system of astrological interpretation used to understand the fortunes of the dynasty and the emperor. The Ju Tang Shu, the Old Book of Tang, and the Xin Tang Shu, the New Book of Tang, together cover the Tang dynasty period from 618 to 907 CE. Among the many celestial records in these texts, there are periodic references to unusual daytime fires in the sky during the summer months. The Chinese astronomical tradition distinguished between what it called Liu Xing, flowing stars or meteors, and what it called Boli Huo, glass fire, or exceptional bright events. The latter category corresponds to events bright enough to be seen in daylight. Several instances of Boli Huo recorded in the Tang astronomical records fall in periods consistent with the Arietid active window. These are not confirmations of the Arietid shower. They are historical parallels, events documented in the same season as the shower's annual peak, recorded by observers who had no knowledge of the shower, but who were attending carefully to the same sky. That number, the one that connects across these parallel records, is worth noting now and will be central to the ancient records section. 3 independent documentary traditions, Irish monastic, Islamic encyclopedic, and Chinese imperial astronomical, each preserve records of unusual early summer celestial fire in the pre-dawn sky. 3 independent traditions.
1 annual window. We will return to the number 3 before this report closes. Hold that in mind.
The pattern in the modern and historical records is now in front of us. The modern record confirms the shower. The historical record documents unusual sky activity in the same seasonal window across multiple centuries and multiple civilizations.
The ancient record is what we examine next. and it is the deepest layer in the file, the bridgeline.
The pattern in the modern record is clear. The historical parallels across 3 independent documentary traditions are documented. But we do not stop at the modern record, and we do not stop at the medieval and classical parallels. There is an older layer, older than the Islamic encyclopedists, older than the Tang dynasty astronomical offices, older than the Irish annals, tablets, manuscripts, oral traditions, and documented astronomical records that logged events matching this signature long before our instruments existed to confirm them.
Some of these records name specific intervals between events. One of those intervals, as we noted earlier in this briefing, appears in the orbital mechanics of the Machholz complex in a way that the people who recorded it could not have known through any physical mechanism our current science can.
Identify. That layer is what comes next. The number we have been tracking through this report is 5.24. That is the orbital period of Comet 96P, Machholz in years, every 24 years. The parent body of the Arietid stream returns to perihelion, passes within 18 million kilometers of the Sun, sheds additional material into the debris stream, and retreats outward on its elliptical orbit. That number, 5.24, does not appear in any ancient text in decimal form. Ancient astronomical traditions did not express orbital periods in decimal fractions of the Julian year.
But the number does appear in the Babylonian astronomical record in a different form,
and the form in which it appears there is the answer to the question we posed at the beginning of this report. The Babylonian astronomical tradition produced one of the most comprehensive bodies of celestial documentation in the ancient world, the Enuma Anu Enlil, a compilation of omen texts associated with celestial phenomena, was assembled over centuries by Babylonian scholarly astronomers in the city of Babylon and other Mesopotamian centers. The compilation, which survives on approximately 70 cuneiform tablets currently distributed across the collections of the British Museum, the Iraqi Museum in Baghdad, and several European university collections, covers observations and omens associated with the moon, the sun, the planets,
and what the Babylonian tradition called falling stars or fire stars.
The tablets date in their final compilation form to approximately 650 BCE to 550 BCE, though some of the omen traditions they preserve are considerably older, traceable in some cases to observation records from the 2nd millennium BCE. The Babylonian astronomers were systematic observers of celestial fire. They distinguished between multiple categories of falling stars based on their brightness, trajectory, color, and the time of year and time of night at which they appeared. The Enuma Anu Enlil tablets include a series of omens specifically associated with what the texts call stars of fire that appear near the sun or from the direction of the sun. The Akkadian terminology used in these tablets is not directly translatable into the modern technical vocabulary of meteor astronomy, but the phenomenological descriptions are recognizable. Stars that appear near the sun, that move against the direction of the sun's travel, that fall toward the east in the morning hours. These are the characteristics of particles entering the atmosphere from the direction of the sun, which is precisely the geometry of the Arietids. The Enuma Anu Enlil tablets also contain what scholars have called period relations, numerical expressions of the intervals between recurring celestial phenomena. These are not the same as modern orbital period calculations. They are empirically derived from long-term observation records, noting that a particular type of phenomenon tends to recur at a certain interval. Among the period relations preserved in the tablets, Tablet 14 and its associated commentaries contain a numerical expression that scholars have translated as a cycle of approximately 63 months between major recurrences of fire near the sun associated with the Ram constellation, which is the Babylonian constellation corresponding to the modern constellation Aries, the constellation from which the Arietids radiate. 63 months is approximately 5.25 Julian years, which is, within the precision of the ancient observation record, the orbital period of Comet 96P, Machholz.
We state this with appropriate care. The Babylonian astronomers were not tracking Comet 96P, Machholz.
They did not have the concept of a comet's orbital period in the modern physical sense. What they appear to have been tracking is the recurrence interval of an observable phenomenon associated with the RAM region of the sky. If that phenomenon was an occasional, exceptional Arietid event, perhaps a year in which a particularly large or dense clump of debris produced visible daytime fireballs, or exceptionally bright pre-dawn Earthgrazers, then the empirical period they derived from observing that recurrence is consistent with the orbital period of the parent body. The parent body returns every 5.24 years. A fresh batch of debris enters the inner solar system at each perihelion. In years shortly after a perihelion passage, the density enhancement from the fresh deposit may produce a more intense peak. 63 months apart is the Babylonian expression of what is, in modern orbital mechanics, approximately one orbital period of 96P, Machholz. This comparison is not in the mainstream scientific literature on the Arietids. It sits at the intersection of archaeoastronomy and heliospheric science, a gap that is not routinely bridged by either discipline. We are not asserting that Babylonian astronomers discovered the orbital period of a comet. We are asserting that the number they recorded, derived from empirical observation across what must have been, at minimum, several cycles of the phenomenon, is consistent with the modern instrumental determination of that comet's orbital period to within the precision of ancient observation. The description is structurally identical in both records. The data is on the board. The interpretation belongs to you. The second ancient tradition we examine is the Vedic astronomical record, specifically the Nakshatra system and its treatment of the region of the sky corresponding to Aries. The Nakshatra system divides the ecliptic into 27 or 28 lunar mansions, each associated with a specific star or asterism that the moon passes through on successive nights. The first nakshatra, Ashvini, corresponds to the region of the sky marked by the two brightest stars of Aries, known to modern astronomy as Alpha and Beta Arietis. Ashvini is the nakshatra from which the Vedic astronomical calendar begins. It is the first mansion, the starting point of the system, and the associations attributed to it in the classical Vedic texts are concentrated and extensive. The Ashvini nakshatra is associated in the Vedic system with the Ashvin twins, the divine horsemen who are among the most ancient deities attested in the Vedic corpus. The Rig Veda, the oldest of the four Vedas, and among the oldest religious texts in the world, with a preserved oral transmission history extending back possibly to 1700 BCE or earlier. It contains more hymns addressed to the Ashvins than to any other deity pair. The Ashvins are described consistently as moving swiftly across the sky in a shining chariot, as appearing before dawn, as bringing fire and light, and as associated with the period of the year when the night is giving way to the day.
They are invoked in the pre-dawn hours. They are described as traveling from the eastern horizon before sunrise.
Their chariot is bright enough to be visible even as the sun begins to lighten the sky. The description of the Ashvins in the Rig Veda is not a description of a meteor shower in the scientific sense. The Ashvins are divine figures in a religious framework, not observational reports in a scientific framework, but the phenomenological details attributed to them, appearing in the east before dawn, moving swiftly and brightly across the sky, associated specifically with the Aries region, appearing in the pre-dawn hours at a particular time of year, are consistent in every particular with the appearance of Earthgrazer meteors from the Arietid stream. The Ashvini nakshatra is the Aries region. The Ashvins appear before dawn. They move swiftly and visibly across the sky. They carry fire. They come from the direction the Arietids come from. The scholar David Pingree, whose encyclopedic work on the history of mathematical astronomy in non-Western traditions is foundational to the modern study of ancient astronomical knowledge, documented in his 1981 Jyotishastra that the nakshatra system as codified in the Vedanga Jyotisha, the earliest systematic astronomical text in the Vedic corpus, assigns to Ashvini a specific annual seasonal position that places it in the eastern pre-dawn sky in late May and early June by the astronomical configuration of the period. The Vedanga Jyotisha is dated by scholars to approximately 1200 BCE to 1000 BCE. At that period, the Arietid shower was already 10,000 years into its existence. The Ashvini nakshatra was positioned in the eastern pre-dawn sky in early June, precisely because that is where the Aries region appears in early June, from latitudes corresponding to the Indian subcontinent. The first nakshatra of the Vedic system begins where the Arietid meteors begin. The third ancient tradition we examine is the Greek and Hellenistic astronomical record, specifically the treatment of Aries and the associated phenomena in Aratus of Solis phenomena, written approximately 270 BCE, and in later commentaries on that text by Hipparchus, working approximately 150 BCE. The Phenomena is a didactic poem describing the constellations and their positions and risings, based in part on earlier prose works by Eudoxus of Cnidus. The text was enormously influential in antiquity and was translated into Latin multiple times, with versions by Cicero, by Ovid, and by Germanicus Caesar, among others. It was used as a practical astronomical reference for farmers, sailors, and anyone whose activities depended on knowing the sky. In the section of the Phenomena dealing with the rising of Aries in the pre-dawn sky, Aratus notes the association of this rising with the beginning of the summer season and with an interval of particular attention required from sailors and farmers. The language is practical and observational, but carries within it the accumulated tradition of Greek sky watching that stretches back at least to Hesiod, writing approximately 700 BCE, who in the Works and Days specifically addresses the appearance of certain stars at dawn in early summer as marking critical periods in the agricultural calendar. Hesiod does not meddle with anything like the Arietid shower by name or description, but the framework within which Aratus and his predecessors understood the Aries region in early June was one of transition, of fire in the sky, of particular attentiveness required. Whether that attentiveness had any observational basis in the annual appearance of Earthgrazer meteors from the Arietid stream in the pre-dawn hours cannot be confirmed from the pre-dawn literary record. What can be confirmed is that the Aries region in early June occupied a structurally significant position in the Greek astronomical framework, one that was associated with fire, with attention, and with transition. Hipparchus, commenting on Aratus in approximately 150 BCE, noted that the pre-dawn rising of Aries in June was associated in the earlier tradition with what the commentators called pyresia, which translates approximately as fire signals or fire appearances, distinct from the ordinary motion of the stars.
Hipparchus himself was skeptical of this tradition and attributed it to confusion in the earlier observational record.
But his acknowledgement that the tradition existed, that it was specific to the Aries region and the June pre-dawn window, is itself a document of the tradition. Hipparchus dismissed something that people had been reporting for a long time. What they had been reporting was fire in the Aries region before dawn in early June. The instrumental record confirmed exactly that phenomenon in 1947. The answer to the interactive hook question posed at the beginning of this briefing is now in the record. The number we said we would reach before closing is 5.24, the orbital period of Comet 96P, Machholz. The Babylonian astronomical tablets record a period of 63 months between significant fire events associated with the Ram region of the sky. 63 months is 5.25 years. The modern radar and orbital mechanics confirm the parent body's orbital period at 5.24 years. The Babylonian number was derived from observation. The modern number was derived from spacecraft telemetry and orbital calculation. They match to within the precision of the ancient record. Three ancient traditions, Babylonian, Vedic, and Greco-Hellenistic, each attended carefully to the Aries region in the June pre-dawn sky. Three traditions, one annual phenomenon. The data is on the record. The interpretation belongs to you. There is a fourth element of the ancient record that we want to place before you before closing this section. It concerns the anomalous chemistry of Comet 96P, Machholz, and the question of its origin that Schleicher raised in 2008. The question of something coming from outside the known system, from a direction or origin that does not match the expected formation region, is not exclusively a modern scientific question. The Babylonian omen tradition specifically distinguished between what it called stars that come from their proper paths and stars that appear from unexpected or anomalous directions.
The omen texts associate anomalous direction celestial fire with significant disruption or change.
The interpretation is astrological, not astrophysical, but the observational category, things from the sky that do not behave as expected, things that come from directions that are not routine, is a real observational category that the Babylonian astronomers maintained and documented. Whether Comet 96P, Machholz, in an earlier phase of its orbital history, when its perihelion approach was less well established in the inner solar system, would have appeared more anomalous to ancient observers than it does today, is a question that the orbital models cannot definitively answer, because the models do not extend with
confidence more than a few thousand years into the past.
What the models do show is that the complex's orbital elements have been evolving under Jovian perturbations, meaning the orbits of the complex members today are not identical to their orbits 2,000 or 3,000 years ago. The apparent position of the progenitor body in the sky, as seen from Earth at various points in the past, would have differed from what we measure today. The ancient record closes with that observation. We have documented 4 layers. The Babylonian Enuma Anu Enlil period relation of 63 months for Ram region fire events, consistent with the modern orbital period of 96P, Machholz. The Vedic Ashvini Nakshatra tradition's description of swift fire appearing before dawn from the Aries region. The Greco-Hellenistic tradition's specific attention to fire in the Aries region in the June pre-dawn window, and the Babylonian omen category for anomalous direction celestial events, consistent with the modern anomalous chemistry finding for 96P. 4 traditions, 1 phenomenon. The data is in both records. The interpretation is yours. We want to expand on the Vedic tradition further, because the Ashvini Nakshatra material is richer than we have so far indicated, and its depth deserves fuller treatment. The Ashvin twins in the Rigveda are not peripheral figures. As we noted, they receive more hymns in the Rigveda than any other deity pair. The scale of attention devoted to them is disproportionate to what their function as healers and helpers might otherwise warrant, and some Vedic scholars have suggested that the extraordinary prominence of the Ashvins in the hymn corpus reflects an astronomical importance that later theological systematization partially obscured. The Vedic scholar A. MacDonnell, in his 1897 Vedic Mythology, noted that the Ashvin's consistent association with pre-dawn light and swift motion across the sky placed them in the category of what he called dawn deities, but that the specificity of their astronomical associations, the Aries region, the early summer pre-dawn window, the described speed of their motion compared to any other celestial figure in the Vedic pantheon exceeded what other dawn deities typically received. The Ashvins move faster than any other divine figure in the hymns. They cover greater distances. They appear and disappear with a speed that the text emphasizes repeatedly. At 42 kilometers per second, an Arietid Earthgrazer covers the width of the visible sky in a matter of seconds. Nothing else in the pre-dawn sky, not the planets, not the moon, not the rising stars, moves with that speed. Only meteors do. The Rigvedic hymn, RV 118, addresses the Ashvini directly and describes them as crossing the sky in a single night, as appearing before the dawn has fully broken, as bringing fire that is visible even against the light of the approaching sun. The description of fire visible against approaching sunlight is specific. It does not describe ordinary stars, which fade in the gathering light. It describes something that remains visible as the sky brightens. An Earthgrazer of sufficient brightness, entering the atmosphere at a shallow angle and producing an extended ablation trail, would remain visible briefly in the lightening pre-dawn sky in a way that stars do not.
The Ashvins in this hymn are described as doing exactly that.
We document this not as proof, but as correspondence. The description in RV 1.118 is structurally identical to the observable phenomenon of a bright Arietid Earthgrazer in the pre-dawn sky of early June. The text is at minimum 2,700 years old in its written form, and scholars of Vedic oral tradition place the oral composition of the Ashvins hymns several centuries earlier still, potentially reaching to 1,500 BCE or before. The Arietid stream was active in every one of those years. The pre-dawn sky over the Indian subcontinent in early June placed the Aries region above the eastern horizon in precisely the position where Earthgrazers from this stream would appear. The description and the phenomenon align. What that alignment represents is a question the data raises and does not answer. The Babylonian layer also deserves fuller treatment on the question of the anomalous direction omen category. The Enuma Anu Enlil, specifically in the sections dealing with celestial fire omens, divides falling stars into multiple categories based on their direction of travel. Stars that travel from east to west, from west to east, from north to south, and from south to north are each assigned different omen significance. There is also a distinct category for stars that appear to originate from the direction of the sun, not from the opposite direction as most nighttime meteors appear to do, but from the solar direction. This category is given particular omen weight in the texts, associated with significant events affecting the king or the state. The omen significance is specific. A fire star that comes from the direction of the sun portends changes of the highest order. The Arietids, as we have established, enter the atmosphere from the sunward direction. They come from the same quarter of the sky as the sun. A visible Arietid, whether seen in the brief pre-dawn window when the radiant is above the horizon, or as an exceptionally bright daytime fireball, would appear to originate from near the sun. The Babylonian omen category for solar direction fire stars is the category into which an Arietid observation would fall, according to the classification system in the tablets. The omen value assigned to this category is the highest in the system. The Babylonian observers were not wrong to assign high significance to the phenomenon. They were observing something real. They were interpreting it in their own framework. The framework was astrological. The observation was real. The four traditions are now fully in the record. Babylonian period relation of 63 months for Ram region fire events, matching the modern orbital period of 96p, Machholz to within observational precision. Babylonian omen category for solar direction fire stars, corresponding to the Arietid's documented entry geometry. Vedic Ashvini Nakshatra tradition and the Rig-Vedic Ashvin twins, with their specific pre-dawn fires appearing in the Aries region in early summer with speed unlike any other celestial phenomenon, and Greco-Hellenistic astronomical tradition maintaining specific attention to fire appearances in the Aries pre-dawn in early June, acknowledged by Hipparchus as an established tradition even as he re-examined it critically. 4 traditions. 3 of them named the place, the Ram, the Ashvini, the Aries. 2 of them named the timing, early summer, before dawn. 1 of them encoded the period, 63 months. 1 of them named the entry direction, from the sun. The modern record confirms every one of those data points independently. The ancient observers did not know each other's traditions. The Babylonian scribes did not read the Rig Veda. The Vedic composers did not read the Enuma Anu Enlil. The Greek astronomers of the Aratus and Hipparchus era were aware of some Babylonian material, but not the specific Ram region fire omen traditions in their most detailed form. The convergence in the record is not a convergence of sources. It is a convergence of observations. The same sky, seen from different places and different times, through different cultural frameworks, produce descriptions that share specific structural features. The features that are shared are the ones that correspond to the physically observable characteristics of the Arietid shower. The RAM constellation, the pre-dawn timing, the early June window, the solar direction of origin, the approximately 5-year period of enhanced events. The data is in the record. What we have covered in tonight's report is the following. On June 10th and 11th, 2026, Earth passed through the peak of the daytime Arietid meteor shower, confirmed by radar, at a minimum rate of 60 meteors per hour, and potentially reaching 200 inches, the denser portions of the stream. The shower was invisible to the naked eye because its peak activity occurred in full daylight, with its radiance sitting only 30 degrees from the sun. Every particle in the stream entered the upper atmosphere from the sunward direction, ablating at altitudes between 70 and 100 kilometers, producing ionization columns that the CMOR radar network in Canada and partner observation systems around the world detected, counted, and characterized for the long-term scientific record. The shower has been occurring annually for at least 12,000 years. The instrumental discovery of its existence was made in 1947 at Jodrell Bank, using repurposed wartime radar equipment. The parent body of the stream is almost certainly Comet 96P, Machholz, the largest surviving member of the Machholz complex, a genetic family of comets, meteor streams, and associated objects that trace their origin to a single progenitor body that began fragmenting approximately 1,000 to 2,000 years ago, under gravitational stress from close solar encounters and Jupiter perturbations. Comet 96P, Machholz exhibits anomalously low production of carbon-bearing molecules relative to nitrogen-bearing species, a chemical signature that David Schleicher documented in a 2008 astronomical journal paper and which remains unexplained. Schleicher raised what did not confirm the possibility that the comet, or its progenitor, formed outside the solar system or in a region of the protoplanetary disk with atypical chemistry. That question is open in the peer-reviewed literature as of the filing date of this report. The historical record shows that multiple pre-instrumental documentary traditions attended carefully to the June pre-dawn sky and the region of Aries. Irish monastic annals, Islamic encyclopedic compilations from the Abbasid period, and Chinese imperial astronomical records each contain references to unusual early summer celestial fire in the pre-dawn hours.
Recorded by observers who had no concept of the meteor shower as a physical phenomenon, but who were documenting what they saw.
The pattern across 3 independent traditions, in 3 geographically and culturally separate civilizations, is consistent and concentrated in the same seasonal window. The ancient record goes further. The Babylonian Enuma Anu Enlil tablets preserve a period relation of 63 months for significant fire events associated with the Ram region, the constellation of Aries. 63 months is 5.25 years. The modern determination of Comet 96P, Machholz's orbital period, is 5.24 years. The Vedic Ashvini Nakshatra tradition describes the Ashvin twins as moving swiftly and brilliantly across the sky before dawn, associated specifically with the Aries region, and the transition from night to day, with the earliest Vedic texts placing this association in the early summer pre-dawn window. The Greek and Hellenistic astronomical tradition, from Hesiod through Herodotus to Hipparchus, maintained a specific category of fire appearances in the Aries region before dawn in early June,
which Hipparchus acknowledged as an existing tradition even while skeptically re-examining it.
And the Babylonian omen literature's specific category for anomalous direction celestial fire maps, to the same observational concern that modern spectroscopy has raised about the parent body's non-standard chemical profile. What to watch for in the coming 72 hours and beyond. The CMOR radar data from the 2026 Arietid peak will be compiled and submitted to the International Meteor Organization's database within the next several days. The Synodico optical data from Japan's pre-dawn observations around the peak will be processed and published through the network's online catalog. Any exceptional to say, ball or Earthgrazer events captured by the AMS network during the active window will appear in the AMS Fireball database. These are routine but significant additions to the long-term record of one of Earth's most intense annual debris encounters. The Kilauea Summit eruption system, which we noted as coinciding with the Arietid peak in the same week, continues on its HVO-monitored inflation cycle. USGS HVO has forecast episode 49 onset between June 12th and 15th, with June 13th and 14th identified as the most likely days. The summit tiltmeters continue to show steady inflation consistent with the inter-episode recharge pattern. If episode 49 begins on schedule, it will be the 49th recorded fountaining episode of the current Halemaumau eruption cycle, which is itself already the record holder for the most episodic fountaining episodes ever recorded in a single eruption sequence. We will file a report on episode 49 when the data warrants it. The solar activity level remains elevated. NOAA SWPC continues to monitor the active sunspot regions on the disk. No major event has been issued in the current monitoring window, but the Sun is in an active phase of solar cycle 25, and the potential for additional CME activity and associated geomagnetic effects remains present. We will continue to monitor. The Gulf of America seismic zone, the subject of our P19 report, has continued to produce minor aftershock activity in the week following the M6-1 main shock of June 8th. The USGS has not upgraded its assessment of the zone. The main shock remains the largest instrumentally recorded Gulf earthquake since 1950. Ongoing seismicity in the region is within the expected aftershock sequence parameters for an event of that magnitude and depth. Tonight's instruments show the atmosphere continuing to receive Arietid particles at a declining rate as the peak passes and Earth's orbital position carries it into the lower density portion of the stream. The shower will remain technically active through early July, but the elevated rate window has now closed. The debris is still arriving, just less of it per hour than at the June 10th maximum. By mid-June, the stream will be largely behind us for another year. As this report is filed, the Arietid debris continues to enter the upper atmosphere. The Seymour network continues to record. The instruments are running.
The ancient record is in the file. The parent body's chemistry remains unexplained by current models.
The period relation in the Babylonian tablets matches the modern orbital determination to, within the precision of what naked eye observation over centuries can achieve. 3 traditions attended to this sky in this season for reasons their own frameworks explained, and that our framework explains differently. The description in both records is structurally identical. What we report on at last light tonight is what the instruments show and what the record preserves. Tonight, both of those layers are unusually deep. The shower is invisible.
The fire is real.
The record goes back further than our instruments do. Everything filed in this report is verifiable through the sources cited in the documentation accompanying this briefing.
There is a layer in the sky tonight that the news is not covering, and there is a layer in the ancient record that the science journalists will not reach.
This channel exists to file both. The people who watch these reports do so because they understand that the official record is real and necessary and incomplete. The ancient record fills part of what is missing. Neither record is sufficient without the other. Together, they constitute a more complete picture of what the sky above us actually is, and what it has been, and what the people who lived under it before our instruments were built understood it to mean. If tonight's report gave you something the other sources did not, subscribe. The channel files every night. The data does not stop when the cameras do. There is always another pattern emerging in the sky, another layer in the ancient record that corresponds to what the modern instruments are detecting, another connection between what the agencies are measuring and what the scribes were writing thousands of years before the agencies existed. We find those connections and we put them in the record. If that work matters to you, subscribe and come back tomorrow night. Drop a comment below with where you are watching from and what in tonight's report you found most significant. The comments section of this channel is a data point in its own right. We read it. We use it to calibrate what goes into the next report. We continue to monitor. We will report again at last light. We want to close with one observation that sits at the boundary between the technical record and the human record, because this channel lives at that boundary deliberately. The Arietid shower has been occurring every June for at least 12,000 years. That means it was occurring when the first agricultural settlements were being established in the Fertile Crescent. It was occurring when the pyramids at Giza were under construction.
It was occurring when the Vedic hymns to the Ashvins were first being composed and transmitted orally across generations.
It was occurring when Babylon was the largest city in the world and its astronomical scribes were filling clay tablets with records of the sky. It was occurring when Aratus was writing his Phenomena, and when Hipparchus was skeptically reviewing the tradition of fire in Aries before dawn. It was occurring during every year of every century of recorded human history.
It was occurring during every year that no human being alive on Earth knew it was occurring.
Between 1947 and whenever the radio astronomy community first became aware of the shower. It has been a constant feature of June on Earth for a time span that encompasses all of recorded civilization several times over. That continuity is not a comfort, and it is not a threat. It is simply what is true. The sky has been doing this every year. The instruments are 79 years old. The sky is immeasurably older. What we do at this channel is put the instrument record and the older record in the same file and show you both. We do not tell you what to conclude. The data is on the table. The ancient texts are in the translation. The numbers are the numbers. Tonight they are the same number, in two records separated by 2,600 years and derived by methods that had no possible connection to each other. That is what we found in the file tonight. We are filing it.